So today we'll continue to talk about the fundamental of waves, and then after that we'll go into quantum mechanics. So previously, last week, if you guys remember, one thing I want to mention beforehand is that I saw only probably 3 of you participate in the office hour Dodo's poll. Please fill that out because we want to figure out a time as soon as possible. And then the second thing is that for the homework, so the first homework will be released tomorrow, and then ideally, I would say for any homework, I prefer students to finish like within a week, right? So that you're still fresh, and then if you have any questions, you can ask them, and then that actually help your class. But I also understand that this semester is very special, and then some of you might occasionally run be caught up with other things, right? So the official deadline we'll give you guys is that at the time of I post a homework, you will have at least 2 weekends, to finish your homework. But I encourage you to finish that within a week, just to help yourself to keep up with the class. Okay. Now let's come back here. Last week, we briefly talked about the fundamental of waves, and then I think a few things we know is that first is that to describe a wave, you need to write down the amplitude of the wave, and then the amplitude of the wave is a function of position and time. So you describe, for example, the water wave. It describes the amplitude of the water fluctuation of the entire space and the entire time, x, y, z, and then t. And then second, we know that for the wave compared with the particle, instead of using F equals ma, what we do is that we have a differential equation on your amplitude or on your field. And then we give one example, that is the longitude wave, the mechanical wave. A lot of particles, and then they interact with each other, the nearby neighbor. And then for this model, we have this differential equation where EMP is the stiffness of the spring, and then rho is the density, one-dimensional density of the of your material. So this is the a typical wave equation. That is a differential equation, and then the way to think about this is that a differential equation usually for a wave must have differential of time and also differential of place. So the differential of time, you can imagine anything that you take a second derivative is equivalent to a, right, acceleration, because acceleration is the second derivative of place, right? So this part is ma, and this part, what is this part? This part is this part is your F. Right, the way to understand this is that if you have energy, then you do a derivative, then that gives you force. And then here, because the force is the space difference between nearby particles, so you have to do a second derivative. So, and the derivative on space, you can in general interpret that as a force, and then the derivative on time, you can understand that as your acceleration. And of course, all this understanding is just to help you to picture the wave. If you have difficult time, like when you look at differential equation at first, if you're not familiar with it, you might get lost. So this is just a way to picture this wave. Just to build a connection between this and then the particle physics you learned before. But in reality, when you get used to solving differential equations, then this is just math. It's just math. It doesn't really mean anything, and then it doesn't have to mean anything. Okay, and then this is what you will learn in quantum mechanics. Okay, not every equation has to mean something. Not every mathematical derivation has to mean something in physics. And then I think next what we get is that the solution for this, or solution for most simple plane wave equation, would be cosine omega t plus minus kx, and then sine omega t plus minus kx, right? And then we explain that omega is the angular frequency, and then k is the wave vector, which is like the frequency in terms of space. Okay, and then any omega and any k, well, not any omega, any k. And then the omega and k, they have to follow this relation, is that if you plug this back into this wave equation, then you get omega divided by k equals, okay, equals this, right? And previously we explained that, okay, this is actually the velocity of the wave. Okay, omega divided by k, when you look at how the wave propagate and how the wave evolve in time, you see omega divided by k is actually velocity. And then when you plug this back into the wave equation, you also see that omega divided by k is the Young's modulus divided by your density, square root of that. Okay, so what it tells you is that, okay, if you plug this back into here, and the wave equation will look like v squared okay. So the wave equation, the coefficient, actually represent the speed of your wave. Okay, I don't know how many of you have taken the EM field, but in the EM field, so probably the best well-known, the best known story, okay, of the speed of a wave is actually the speed of the light, right? I don't know if you guys know how Maxwell proved light is EM wave. The logic is quite simple. So Maxwell used Maxwell equation, and then he solved the equation of wave, right? And then he solved a differential equation, and then there's a velocity showed up. And then the velocity is determined by the epsilon and mu. Okay, epsilon and mu in the Maxwell equation, epsilon exists in the electrical field equation, mu in the magnetic field equation. Okay, and then when he calculated the velocity of this electromagnetic wave, it turns out that it's very close to the speed of light, which people have already measured at that time. Okay, and then so he conclude that, okay, because the velocity is so close, that the electromagnetic wave has to be well, because the velocity is so close, the light has to be one kind. Okay, 1 second. Let me see. I'm not sure why. It also happens last time, right? Yeah, probably I should replace the HDMI cable. Okay, so yeah, so because the speed of electromagnetic wave he solved in Maxwell equation is very close to the light wave. Okay, it's the speed of the light wave people measured in experiment, so that he concluded that light has to be an electromagnetic wave. Okay, that was the reasoning behind why light is EM wave. And then of course there's further experiment there, right? People generate EM wave at radio frequency, and then that's actually the famous experiment. And then people start to use that as to build telephone, etc. Okay. Now let's move on here. Today we're going to talk about three, I would say, must-know things for wave equation. And then the first one is what we call linear, or linearity of the wave equation. So the equation, okay, we're going to see in this semester or in most quantum mechanics textbook is a linear equation, linear differential equation. So the linear is actually very important. And how do we define linear? Linear, I don't know if you guys learn linear algebra, but then in linear algebra, the definition of linear is that if this, we can rewrite this equation, okay, we can move this to the left-hand side as well. So you have partial differential of time minus E rho differential of space. This is called an operator, right? Operation of a function, and the function is u x t. Okay, so the notation here is that this is an operator. They operate on u. Okay, so you differential this, you differential that, and then this is equal 0. Okay, this is the same equation as we have for the longitude mechanical wave. And if we define this as, let's say, an operator O, okay, we say that, okay, the equation, differential equation can be represented as a differential equation operator. Well, let's use D. D is easier. D means differential. Let's say these two, the entire thing inside the bracket, let's call it D. Okay, so we have D act on your wave function is 0. Okay, so the linearization means that if you have one solution of this equation, if you find one solution, and then let's say you find another solution, right? We indeed find two set of solutions, right? Cosine and sine. And then also we can change the k and omega as long as omega divided by k equals speed of the wave, right? So in principle, we actually have infinite number of solutions here, okay? So linearization means that, okay, if you find two solutions, if you find two solutions to this differential equation, then the linear combination right? The linear combination, you multiply A in front of U1, multiply B in front of U2, right? This is a linear combination of your solutions, must also be the solution to this differential equation. Okay, so if you find any solution, this is true for any solution you can find to the differential equation. Okay, as long as you satisfy this, we say that this equation, this differential equation, is linear. Is there any question here? Okay, everyone understand this concept? Okay, good. So this is actually, the way to prove this is super simple, right? You just see, okay, this equals 0. This also equals 0, right? So you plus these two, it would just be A, D, mu1 plus B, D, mu2, okay? So equals to A times 0 plus B times 0, of course, still 0, right? It's always, as long as you are the solution to the differential equation, then you always satisfy this differential equation. So operator act on your wave function equals 0. Okay, now no matter how many zeros you add together, you always end up with 0, right? So that's why you can always see that the linear combination of the wave solutions are still the solution to this equation. And this is actually the foundation of the Young double slit experiment, right? In the Young double slit experiment, if you guys recall, okay, there's a light coming in here, the first slit, and this become a point source, and then the second one is two slit, and then this is a screen, and then you have 2 point sources here. Okay, and then you will have let's see. And when we're calculating the Young double slit experiment, we say that the electrical field arrived here, E, okay, is the sum of, if this is slit 1, slit 2, E1, let's say cosine KL1, the distance here is L2, okay, plus E2 cosine KL2. And we say that, okay, if the distance happen to be that this is 180 degree off, okay, cosine KL1 plus cosine KL1 plus pi, then these two cancel each other, right? That's why you can see dark spot, okay, on this on the Young double slit screen, okay, and there we just, well, I guess in high school we just tell you that you can add 2 waves together, right? We just tell you that. But the physics behind it is that the light obey Maxwell equation, and you can prove that Maxwell equation when you write in the waveform they're linear, and thus you can add 2 light together. Okay, you can add 2 light wave together directly together. Okay, and you might wonder, okay, is there any wave that is there any differential equation that is not linear? Okay, that is not linear, and there are actually many examples, and let's see. One very simple one, let me give an example here, is that if you still have this, but instead of equal to 0, equals to, let's say, u squared. And this is not linear. Why is it not linear? It's because if you try to do like u1 plus u2, right? If you have 2 solutions, and then you add them together, you try to put it back and see whether this is still the solution to this differential equation. You will see left-hand side is exactly the same. Okay, the right-hand side, but you now have u1 plus u2 squared equals u1 squared plus u2 squared plus 2 u1 u2. Right? There's a cross term. There's a cross term exists here, and this cross term would not exist if you are only u1 or if you are only u2. Right? So this is what this means in physics, is that these 2 waves are interacting. Okay, there's a term that the magnitude depend on both the wave 1 and then on both wave 1 and wave 2. Okay, that means these 2 waves are interacting. So the way to see this nonlinear behavior is actually very simple. If you throw 2 rocks into a pond, and then you see that water wave propagate, that's linear. You can see them cross each other and then create some interference fringes. But then if you go to the ocean and then you see 2 waves crash, okay, then you see chaos. Okay, you don't see 2 interference patterns, you see 2 waves crash into each other and then collapse and then completely chaos. In that case, that is nonlinear. And you might wonder, okay, but they are both waters, right? How can you have the water in the pond is linear, but then the water in the ocean is not? The answer to that is that as long as your wave is the magnitude of the amplitude of your wave is very small, then anything can be linear, right? Because if you look at these terms, they're square to your amplitude. Okay, let's say if your amplitude is 0.1, then everything on this side scales with 0.1, but then here you have been 0.01, right? You square it. Then this side is like 1 magnitude smaller than that side. and then the nonlinear effect doesn't really matter that much. Okay, but if you think about it instead, your amplitude of the wave on this side is 10, right? Then this side will be 100. So your nonlinear term is 100 times larger than your linear term. Sorry, 10 times larger than your linear term. So that the entire behavior of the wave will be determined by the nonlinearity. So that's why when you see two, ocean wave, when they collide, it's completely chaos. Okay, that's because it's dominated by this side. Where in the pond, the amplitude is so small, so that it's completely dominated by the linear term here. Okay, and in this quantum mechanics class, you would not have to worry about nonlinearity. Okay, the reason is very simple. There is no, it's very hard to find a nonlinear quantum mechanics wave equation that you guys can solve. Okay, like you can solve in 2 hours. It just doesn't exist, right? So we will not talk about nonlinear wave in this class, but just want you to know that they exist. Okay. Any questions about the linearity of the wave? Okay, so you guys all accept that as long as you have, you have multiple solutions, and then you can add them together linearly, and then there's still the solution to the wave equation. Okay, and okay, then let's move on to the next one. Let's see. Okay, so let me ask you guys a question, right? So this is the wave equation, and then this is a solution, and then we say you can choose any frequency as long as frequency divided by the wave vector equals the speed of the sound, right? This is a mechanical wave, which is sound wave. Now the question is, okay, some of you must have played like guitar or violin, and why does the string has a certain sound? Certain sound means that it has one frequency, right? Why it doesn't have all this type of frequency? You can have all kinds of frequency according to the wave equation, but why your guitar, when you play a certain string, right, it only have one sound? Why is that?
Its tension and length are fixed.
Yeah, lengths are fixed, right? And that's how actually you change the sound of the guitar, right? You push the other finger at different spot. You change the length of the guitar, and then the sound will be different. So in a physics term, what that means is that means your wave equation need a boundary condition, right? The boundary condition. Okay. So for example, this is a guitar, and then the two end is fixed, right? So when the two end is fixed, the boundary condition is written as U x equals 0. Let's say this is x, and the length is L, right? X equals 0 at any given time is always 0, right? It's fixed. And then the same condition for the right side. Okay, you have U when x equals L, right? The string doesn't move at that fixed point. So this is called boundary condition. So whatever solution you have here, it has to satisfy the boundary condition. Otherwise, it's not a solution to this wave equation. Okay, if you don't have boundary condition, then what you're solving an infinite long string, and then it's floating on both sides, right? So there's no boundary condition. It's like you can let go of the string, and the string can do whatever they want. that is a wave equation without boundary condition. But in reality, all of the strings or all of the wave that we're looking at, it has some constraint, and that constraint is the boundary condition you pick here. Okay, so how could that narrow down our solution? We have a boundary condition in position, right? Does anyone know that, what to do in this situation for a differential equation? Anyone wants to give a try? Okay. So in a standard way, it's actually separation of variable, right? So take a look. This wave function is a function of x and a function of t, right? So you can separate that as function of x times a function of t. Okay, and then by doing that, you can solve these components and then match the boundary condition. That one is, taught in a mathematics class, and then I don't want to go too much into here. But then there's another way to solve this, and because in this class most of our wave equations are very trivial. Okay, so actually you don't have to know this to be able to solve this. Okay, so if you look at this string, and then if you look at our wave solution, the primary problem, okay, of putting this into here is that it's not just that x equals 0 is 0, but it's that when x equals 0, no matter what time you're at, it's always 0, right? So if you take a look at these two solutions here, at times equals 0, this equation becomes sine omega t, right? So it's oscillating with time. This solution becomes cosine omega t at x equals 0, right? So it's oscillating with time again, right? So how can you get rid of the time? All right, how can you get rid of time? And the way to think about it is that, okay, if you have sine omega t, and then how can you make it to 0 at any time? And if you know enough about function, okay, a function of t, if you want to get this to 0, there's only one way. Okay, there's only one way. It's to minus sine omega t. Okay, so this is always 0. But then you say, okay, this doesn't even make any sense, right? You're just giving me a function that equals to 0. But then you actually have two functions, right? One is sine omega t plus kx. The other is sine omega t minus kx, right? So you actually have two functions. And then when x equals 0, these two functions becomes the same, right? So when you write down sine omega t minus sine omega t, you can actually make it look like sine omega t minus kx minus sine omega t plus kx. Okay, now this is not a trivial 0 function, right? This is a legit function that satisfies the boundary condition at x equals 0. Right? Does that make sense? Okay, and then you can do the same thing to cosine, right? You can do the same thing to say cosine omega t minus kx minus cosine omega t plus kx, right? At position x equals 0, you still have cosine omega t minus cosine omega t, so it's always 0. So this form of solution always satisfies the boundary condition on the left. Okay. And then, in case any one of you actually know separation of variable, you probably are wondering, okay, how does this convert to this form, right? You now have a function that is both a function of time and position. How do you convert it into a function of position times a function of time, right? That's the standard mathematical way to solve this equation. And the trick here is to use the, it's just to do a simple, a Google search, and then you know that there's this equation exists. I don't know if, I think this is, well, it's not my job to teach how to prove this, so you just believe me and then believe Wikipedia. Sine alpha minus sine beta, okay, alpha beta equals to cosine alpha plus beta divided by 2, and then sine alpha minus beta divided by 2. Okay, so when you see a sine and a cosine, well, there's many variation of this, right? So when you see sine plus minus another sine or cosine, you can always use this type of equation. You can look up in Wikipedia, and then to simplify it, okay, to simplify it, and the result is very obvious, right? So if you have alpha plus beta, this is alpha, this is beta, right? Then the position cancel each other. Minus kx cancel kx. Omega stay, right? And then divided by 2. So this is omega t plus omega t is 2 omega t, but then you are divided by 2. So you get omega t instead, right? So it's 2 cosine omega t. Okay, this is the first term. And the second term is sine alpha minus beta. Alpha minus beta is minus kx, right? So it's actually minus 2kx, and then divided by 2. All right, sine minus sine of the sine come out first, so sine kx. And then we know that the amplitude actually doesn't matter because you can add any amplitude and then it's still the solution to the wave function. Okay, so this is one solution set, and then you can see that, okay, you have a function that is a function of time times a function of position, right? So any solution you get, you can kind of transfer it into the separation of variable eventually. Okay, eventually. And then here it's the same. This one you will get sine omega t sine kx, right? And this actually makes sense, right? If you think about it, sine kx always start, well, at position x, it's always 0, right? So it's very safe to use sine kx as a solution. Okay, now let's think about the boundary condition on the right. So it's similar, right? It says that at position L, at any time, that this the amplitude of the wave is 0, right? Because the point is fixed. So if you look at these two possible solutions here, cosine omega t sine kx, sine omega t sine kx, it's very obvious if you want this to be held for any time, okay, then the only way to satisfy that is sine kx kl, right? X equals L at position L equals 0. Right, if sine kl equals 0, then this solution and this solution automatically satisfy the boundary condition on the right. And how can we get kl equals 0? So this means that kl can be 0 plus minus pi plus minus 2 pi, and then keep going, right? And then keep going. And 0 is a trivial solution. 0 means that there's no wave, right? There's no wave. Sine kl equals 0 means that because L is not 0, so K has to be 0, right? If k is 0, then the entire thing is always 0, which is a solution, but which actually means that the wave is not oscillating at all. And this is one very interesting concept that is actually the key difference between classical mechanics and quantum mechanics, is that in quantum mechanics you actually don't have a solution that is absolute 0. The reason you can think about it, the reason is actually uncertainty principle. Okay, if you have a harmonic oscillator, right? This is a spring, and there's a particle attached to it, and then doing this harmonic oscillation, right? You would think in classical mechanics, the solution will always be, there's a solution that this thing is not oscillating at all, right? Stay at the steady position. But then in quantum mechanics, that's not an option, because in quantum mechanics, you can't know the position and the momentum at the same time. If you're staying still here, what that means is that you know the position at 0 point. You also know that because it's not moving, the momentum is also 0. So position 0, momentum 0. That violates quantum mechanics. Okay. So in quantum mechanics, there's no 0 here. Okay, this is not a solution. So this will be very interesting. Eventually, we'll actually prove to you guys that vacuum is not empty. Okay, by using the same argument, Maxwell equation with uncertainty principle, and then solve Schrodinger equation. You will see that in vacuum actually there is energy. Okay, there's energy in vacuum, and then I know there's right now an ongoing effort to try to prove that this energy from Maxwell equation, okay, at vacuum, is the source for dark energy. Okay, and dark energy right now is a hot topic that people are assuming that the dark energy is, and the dark matter is the reason why the universe is currently in its structure. Okay, it's expanding slightly. Okay, any question about? Yes.
Yeah, I have a quick question. So I have to join the Zoom on like a different device because I'm borrowing something right now. Can I? It won't let me join without a meeting passcode or something.
Oh, the passcode. Let's see the passcode. Let me take a look real quick.
Sorry about that.
I believe the passcode is on the collab.
Yes. Yes, on the collab. I think it's like 2020 quantum or 20F quantum. Can you look it up?
Yeah, I'm on the collab right now, but I'm not sure if is it on the site settings or something.
In announcements, Zoom lecture URL.
Okay, perfect. Thank you.
Yeah.
I can post it in the chat for you if you want. That makes it
Oh yeah,
easier.
that'd be great. Thank you.
Okay. Yeah. Any other questions? Okay, so let's come back here. Let's erase 0 solution here just because it's not interesting. And then what that tells us is that you can arbitrarily select your k. You can select your wave vector arbitrarily. When you choose a fixed length of your string, then your k can only be plus minus pi divided by L, 2 pi divided by L, and actually k can only be plus minus n pi divided by L. Okay, it's fixed by the boundary condition. So the way to picture this is that what this means is that the wave is like this. Okay, can one of you turn off the mic or? Yeah. Okay. So sine, if k equals pi divided by L, you can think it's okay, when x equals L, kx become pi, right? So it's finishing one cycle, half a cycle of 2 pi. So this is 0, this is pi, okay? So this is the waveform of your first solution, and then the second one would be like this, right? Finish from 0 pi to 2 pi. Okay, that's from this one, and then you keep drawing. Okay, keep drawing. And because we know that there's a relation between omega and k, right? We know that omega, the frequency of this oscillation wave, equals k times the velocity, right? So what that tells you is that you can't, well, there's only limited choice for you on the wave vector k. There's also only limited choice for you on the frequency, okay, on the frequency. So that's why when you play your guitar, okay, there's only a certain sound. The sound is, the fundamental sound, pi times your velocity divided by L, and then the multiple octave of that, right? A fundamental frequency, let's say omega naught equals pi v divided by L, and then you have n, so you have 2 omega, 3 omega, 4 omega, and keep going, right? Keep going. So ideally, okay, well, mathematically you can have infinite number of frequencies. You can go to infinite, but then in reality you can't. Well, you won't have that, because for mechanical wave, the reason is very simple. If you increase omega, you also increase k, right? If you take a look here, what it means is that your wavelength keep decreasing, right? And then at a certain point, your oscillation is so fast that it actually violates this model, right? This model assumes that actually has to assume that the displacement is very small. So that's how we can get ui plus 1 minus ui equals to partial u partial x times delta L, right? Delta L is here, right? If you need to do this from differential to this delta, the assumption is always that this has to be small, right? But then if your oscillation frequency is very large, then your oscillation is faster and faster and faster, and eventually what you will have is that you will have this, this is longitude wave, this is transverse wave, but anyway, you have one wave like this, that, right? So the displacement of each molecule to its neighbor become really large, and then you cannot make this approximation anymore, and then this wave equation will fall apart. Okay. Okay. Any questions here? Okay. So our next question is: now we know that the guitar, the string of the guitar, have many different frequencies. Okay, they are all integer multiples of your fundamental frequency. Now the question is, okay, when you play a guitar, why you only hear one sound from one string? Why don't you hear all of these frequencies? Why don't you hear all of these frequencies? Right? You should hear something really high frequency, and then it sounds terrible, right? And then you should hear fundamental frequency and 1 octave, 2nd octave. And why you don't hear all those? You just hear the fundamental frequency. Anyone want to make a guess?
I'm assuming the dominant frequency takes over.
Can you say that again?
The dominant frequency takes over, so you're only really hearing the dominant sound, like the fundamental frequency.
Yeah, but why would the dominant sound to be the fundamental? Like mathematically, it's not that special, right? The fundamental. that's actually the guess in the right direction. Does anyone want to take one step further? Let me ask this. Okay, let's say if you want to predict the motion of the string, is the boundary condition enough? Do you need any other condition?
I would imagine you would need more than just the boundary condition.
Okay, let's draw a comparison. If you're trying to solve the position of the particle, at time t, right? Then what do you need? Do you need to know where it is initially? Anyone want to respond? It's kind of boring to talk to an empty room. If you try to, make me less miserable, you can answer the question. Okay, so for the particle, you actually need to know the initial condition, right? You need to know where it is. You need to know the initial velocity, right? Because the force F equals ma only tells you the acceleration at each moment, right? If you apply the same force, but then initially, let's say I'm 1 meter per second faster than the imaginary friend sitting next to me, then although we're having the same force, but then I will actually go faster than he is, right? Because initially I have more speed. And also the same if two cars are driven at the same velocity or accelerating at the same pace, but then one car is, say, 1 feet away from another car, then he will always be 1 feet ahead, right? So the initial condition actually matters. So it's the same for the wave, right? For the wave, your solution not only have position but also have time, right? To describe a wave, you need position and, your amplitude is a function of position and time. So the initial condition actually matters. And to answer the question, to kind of go one step further from someone's answer previously, the fundamental sound is the dominant sound, right? Why is that? It's because when you pull the string, okay, usually what it looks like, I really should have a marker of different color, but let's say it looked like this, right? You try to lift the string, right? So it looks like it's most close to one cycle, because you rise up from the left part and then reach a maximum at somewhere and then drop to 0 at the right part. Okay, if you think about the second, not the fundamental but twice of the fundamental, then the waveform actually look like this, right? And then we tend to use the word topological too much, but if you look at this two, they are actually fundamentally different, because this one, it rise, drop, cross 0, and then increase again, right? And then the other way to think about this is that if you take the center, right, the fundamental wave is an even function, right? Symmetric left-hand side, right-hand side. The second wave is an odd function, right? It's not the same the left-hand side and right-hand side. And then, so that's why you have one maximum and one minimum. And then the fundamental wave only have one maximum, and that's it, right? So whenever you lift your string, you pull your string, the shape of it look most likely to the fundamental wave. Okay, to the fundamental wave. So that's your initial condition. Your initial condition is close to the fundamental wave. So when you let go, most of the energy will go into the fundamental wave. And then you still have, second order, you still have second, third, a little bit of, all those higher frequency, but you're dominated by the fundamental. Okay. Now, how do we write that down mathematically, right? Okay, so mathematically, the initial condition, okay, you can write it down as u x, my position x, time equals to 0, is a function of position, right? That's your initial condition. And we know that, so from f equals ma, you know that you also have to know the initial velocity. But then there's a very simple trick here, is that you can look at the order of differential. Okay, if you're first order, then you only need to know the initial condition here of, only have to know the initial condition of u. But then if you have a second derivative, then you also have to know the time derivative of u. Okay, this is like velocity, initial velocity of the wave, of the amplitude. Okay, a position, any position x times 0, and then this is another function. Okay, so usually the wave equation that you guys are going to see, for classical wave, it's usually second order derivative. And then in quantum mechanics, they actually become, in Schrodinger equation, is first order derivative. And then also in Dirac equation, is also first order. But there's a case that is second order differential. So that you need to write down the according initial condition. Okay, and then now how do you solve this? How do you map that into our solution here, right? So previously, okay, I erased this solution, but we know that you can only have certain omega and certain k, right? So for any solution you have, it's actually a combination, and the solution form is sine kx cosine omega t, and then also sine kx sine omega t. Right, so you see that sine kx is a common factor, so you can pull that out. So for your solution, you can write it down as, okay, n, and then there's an amplitude n, and then sine, okay, n k knob x. K knob is the fundamental, it's the wave vector of the fundamental wave, according to k knob correspond to n equals 1. Okay, and then we, sorry. Okay, sine n k knob x. Okay, and then we know that there's cosine omega t and sine omega t, and we know that linear combination of them is also the solution, right? So here it would be a n sine n omega naught t plus b n cosine n omega naught t. Right, so it's a linear combination of these two solutions. Okay, and then different a and b go over all the possible combination. Okay, so this is a universal solution set that satisfy the boundary condition. Okay, boundary condition. Then now next you can imagine, okay, see how many free parameters you have here. right? You have an, you have bn, and that's it, right? So the way to get this is to solve an, bn, so that u x t equals 0 equals y x, right? Boundary condition, and then, sorry, initial condition, and then u x t equals 0, the differential here equals z. Okay. So we can use this as an example to take a look. Right, this one, because now time t is always 0, right? Initial condition, we set t is 0, so that sine n omega t goes to 0. So this solution doesn't give us any information about an. An has to come from this equation. This equation is because when you do differential of t, then cosine becomes sine, right? And sine n omega t is 0. So bn, information of bn is not included in this equation. Okay, so each of them solve one set of coefficient. So let's use this, the first one as an example. So what you will get is that you get this is 0, right? So you have sigma n, bn, this is 0, this is 1. Yes, this is 1, okay? bn sine n k x equals to y x. Okay, does anyone recognize this? Equation, a function equals to the sum of a series of sine waves. Someone has to recognize it. Yes, that's Fourier, right? I mean, you guys are engineers. If you don't recognize Fourier, if all of you, none of you recognize Fourier, that would be really weird. So this is just a Fourier series, right? So then what you do is that, okay, if you want to know Bn, what you do is that you do a Fourier series transform on this side, and this side will show as sine k naught x, sine k2 naught x, and then there's an amplitude in front, because you can match them. The other way you can think about this is that you can multiply sine, a certain sine, and do an integration, and then all other terms will disappear but except one of them. Okay, so this is Fourier. Okay, and that's one reason Fourier transformation is useful. Okay, it tells you how to solve the initial condition, how to use initial condition to solve the wave function. Okay, so a little bit summary, and then we're actually done today. So summary here is that, okay, for the wave, I want you guys to remember, although we derive all this using mechanical wave, but then it actually applies to most of the wave, and especially the wave that we're going to solve in quantum mechanics in this class. The first is that to describe a wave, the wave is used amplitude, right? It's a function of position and time. And the second is that to predict the motion of the wave, you don't need f equals ma, you need a differential equation. Okay, differential equation. And then the differential equation has to be a differential of time, and then has to have terms with differential of position, right? One of them is equivalent to ma, the other one is equivalent to the force. Okay, and then when you have the differential equation, you can solve the universal set of the solutions. Okay, in quantum mechanics, this will be called eigenfunctions. And then after that, if you want to completely solve the system, you have to apply boundary condition. Okay, boundary condition to limit the selection of these variables here. And then also you have to apply initial condition, okay, to know how the wave evolve. And then typically when you apply boundary condition, you will see that discrete value show up, right? For example, here the wave has to be n equals 1, 2, 3, and go on, right? The k and omega is no longer continuous, right? There's only a certain number that you can pick. And then when you use initial condition, okay, you have to decide how many of them you have depending on the order of your time derivative, okay? And then that is all for this class today. And then one final word is that I think I forgot to mention in the first class is the form of exam. So the exam will always be take home while you guys are at home. And then the time limit usually is set between 4 hours to 8 hours. And then you will have a week to finish that. Okay, you can count your own time. For example, if the limit is 8 hours, then I usually will give you a chance of 5 breaks, right? So you can start on Monday, do 3 hours, and then you feel you're tired, so you can close the exam and then, let's say, take a break for four days and then redo that. That's fine. And then during that time, you can work on your homework. You can look at your textbook, the notes, the videos, everything. That's fine, as long as you don't work on the exact same problem. Okay, and then you obey the honor code, and then obviously, right? Okay, any questions on this?
I have a question regarding the textbook.
Yes.
Can you like post textbook chapters that go along with our lessons?
You mean like the PDF, or just point to you like which chapter is that?
Just like for instance, for this like fundamental of waves 2, like
Oh,
which chapter to read beforehand.
Oh yeah, okay. So okay, I can try to do that, but the fact is that most of it's not the same as the textbook. For example, this chapter, there's nothing like this in the textbook. And then for the next a few weeks, there's also no corresponding materials on the textbook. The textbook is more like yeah, it's more like a tour book, right? Like it says, okay, this is a Schrodinger equation that's only 1 page, but then we spend actually 2 weeks to explain to you guys why the Schrodinger equation looks like this. And but I will try to do that if I can find, okay, if there's a connection between our lecture, direct connection between our lecture and the textbook. Okay.
Okay, thank you.
Other questions? Okay, then I will stay here for 5 more minutes, and then see you guys on Thursday.
When are the first homeworks going to start coming out? Because I don't see anything in the assignments page right now.
So the homework would be upload to the, I think there's, in the Colab, there's a resource, okay? Will be uploaded there tomorrow.
Okay, and will it be due like every week?
Yes, but then you will be given 2 weeks to finish that. So there will be a weekly homework, and then every homework you will have 2 weeks to finish.
Okay. And then for the homeworks, are we going to be expected to essentially do what you're doing on the whiteboard, like all those derivations, or are they going to be like other types of questions?
So the questions, well, the type of questions will be very diverse, but mostly it's like give you an open question. It's like I write down, let's say I write down a waveform. Okay, tell me the direction of the wave. Is it going left, going right, going up, or going down? Right, and then you have to give analysis, right? You can't just say, okay, it's going left, and then without explaining anything, right? And then it's mostly just testing your understanding of the concept.